Hey gang, this video starts what we call estimation, and just a little bit of a warning. This is a super important video. We're going to find with estimation that calculating the numbers are actually pretty easy, but understanding the underlying concepts, the underlying framework, if you will, is a little bit more complicated. And to be able to work the problems, to be able to be successful in this content, you need to not only be able to calculate the numbers, but also understand where these numbers actually come from, because the homework questions put a lot of twists and turns. Now, again, a little bit of word of advice. We're going to dive deep into the weeds. We're going to go down a lot of rabbit holes here. And if you're just kind of in a mood where you just don't want to listen, I would just stop and just come back to the video later. Take really good notes and try to stay focused as much as possible, because again, this is a little bit more complicated in one sense, and in another sense, if you can just get the framework, I think this is the easiest content that we study in this class. So let's get to it. So in this lesson, we're going to learn to estimate P from P hat, uh, and to estimate mu from X bar. So we're moving into the world of inference. So P and mu, the population values, are now going to be unknown, and we're going to use these values that we calculate from a sample to estimate these unknown values. Now, from the central limit theorem, so what I want to do first of all, I just want to focus solely on proportions for now. So we saw from the central limit theorem that the distribution of distribution of sample proportions will be normally distributed as long as n times p and n times q, you remember n times q is the same thing as n times 1 minus p, are greater than 5. So if all that's greater than 5, then the mean of the distribution is p, and the standard deviation of the distribution is the square root of p times 1 minus p over n, right? So just a little review. Again, central limit theorem plays a huge role in estimation. Now, where are we moving to? We're moving to back to this relationship here between samples and populations. Right now, in the central limit theorem, we are working where P is known, and we can determine the probability of getting an unknown P hat as a sample. We do things like, again, I think we used like 40% of people have a fear of flying. What percentage of people from a sample of 200 or whatever would report they have a fear of flying? We don't know what that would be, but we can determine the probability of an area. Okay, so we're moving the other way. We're now transitioning to estimation. So now we're going to have a sample that is known, that we're going to estimate an unknown value in our population. So again, just to put into words, for estimation, we collect a random sample, we calculate p hat, and we use p hat to estimate p. Now, even though p is unknown, from the central limit theorem, we know its location in the distribution of all sample proportions. It's smack dab in the center, right? We also know the value. Let me put this a little neater here. We also know the value of the standard deviation. It's the square root of p times 1 minus p over n. Now, transitioning into confidence intervals, we're going to find out that sometimes we will always use what we call a level of confidence. And again, confidence intervals are just a technique that we use to estimate an unknown population value. In this illustration, to estimate the unknown population proportion P. There are three common levels of confidence, and those are 90%, 95%, and 99%. I do a lot of work with a lot of research. I read a lot of research. I have never seen a confidence interval other than one of these three reported. In fact, the go-to is always just about 95%, right? I would say that 99.9% of the studies that I have reviewed, confidence intervals have been reported as a 95% confidence. Now, what we got here, we got a chart going on. So what I have in the left part is just the level. So a 90% would be equivalent to 0.90, a 95% would be equivalent to 0.95, and a 99% would be equivalent to 0.99. Now, alpha is just the level subtracted from 1, or this plus this has to be equal to 1. So alpha is, in this case, for 0.90, let me make sure you know those are connected, is 0.10 because those two add up to 1. For 0.95, the alpha is 0.05 because they add up to 1. For 0.99, the alpha is 0.01 because they add up to 1. Now, in calculating these confidence intervals, we need to be able to calculate the z critical. And what we calculate is we calculate z of our alpha divided by 2. And I'll explain why 2 in just a second. So let me get out of this and scoot over to StatCrunch. So if I'm going to go to the calculator, go to normal, my mean is 0, my standard deviation is 1 because I have z-scores. And I need, again, z alpha means area above. And I need the z that has 0.10 divided by 2 above it. Compute that. I'll tell you what, let me do this. This will be much better. Let's go split screen here. All right, so the Z critical for a 90% is 1.645, let's call it. All right, let's calculate the Z critical for a 95%. So what do? 95 goes to 0.95. What number adds to 0.95 to make 1? A 0.05. So we want the Z for the 0.05 divided by 2. Find it. So we get 1.96. Now I have these memorized, but it's not about me. It's about you. I want you to make sure that you understand this. The 99 is the Z 0.01 divided by 2. So we get 2.58. Now, let's just bring in something. What if we wanted 83% confidence interval, and we want to calculate Z alpha over 2? What would we do? Convert to a decimal, right? Alpha is the number that makes this number plus alpha equal 1, right? This becomes Z of 0.17 over 2. 1.37. That's all you have to do. Easy for me to say, right? Okay, so let's move on. We've got these critical values now that we can calculate. And so let's just focus on the 95% and see what goes on in the distribution of sample proportions that we learned in the central limit theorem. So this is made up of a bunch of p-hats, a bunch of sample proportions, right? And we know that the p is smack dab in the center. We know that negative z over alpha over 2 And negative z alpha over 2, again, alpha is going to be 0.05 because 0.05 plus 0.95 is equal to 1. Okay, so we know that the from negative z over alpha over 2 to positive z alpha over 2, we have to have 95% of our distribution. Let's just check it out. 95%. Okay, but since we're not centered at 0, we have to measure our spread right here, not only by the z-score, but also by the standard deviation, because we're residing not in a standard normal distribution, but in a distribution of sample proportions where P is our center. And this defines our variation, this being our standard deviation. So we can't just use the standardized score alone because we're not centered at 0, we're centered at P. And again, our variability is defined by this. So we have to multiply by sigma in each of these cases to get us back into the correct distribution. Now, let's estimate P, which is the percentage of people with a fear of flying. Okay, so let's say we have no idea, and I don't. I've seen some studies, but I don't necessarily have to believe it. So I want to estimate the percentage of people with a fear of flying. So P is the percentage of all people who are afraid of flying or have a fear of flying. I don't know the answer to that. That's what I'm trying to estimate. It is unknown. Let's say we go out, we collect a sample of 492 people, 222 out of the 492. Again, this is just an example. 222 out of the 492 say that they experience a fear of flying. This is my sample proportion. I'm going to use this to estimate P. Now, let's estimate with 95% confidence. Now, here's where things get kind of crazy. Let me pull up the previous. All right, so I come in here and I just end up at random getting a P hat. Now, when I get a P hat, is it above P or below P? I have no idea because I don't know where P is. I know in theory it exists. I know it's in the center of my distribution, but I don't know if P is above it or below it. I just know that the P hat is somewhere in here. Now, I've drawn this thing, this kind of legend here, if you will, to give me the center of the distribution, the left end and the right end. Now, let's move that to the center of my P hat. And if I create an interval there, is P what I'm looking for in that interval? Well, yeah, it is, right? What if I choose a P down here? The P that I get just happens to be down here. And again, I don't know where my P is. So if I center around there, my confidence interval, I'm going to make it bigger to distinguish it from, and it's off the table, so I can't do much with it. But the important part is, does this P fall in this interval? It doesn't, right? So I can be positive that when I pull out a sample proportion at random, if I get one from here to here, this interval that I'm drawing around the P will contain, I'm sorry, the interval I'm drawing around the P hat will contain the P that I'm trying to estimate. The only time it doesn't include P is if I get something down here in the tails. And there's only a 0.025 probability of getting something down here and a 0.025 probability of getting something up here. So there's only a 0.05 probability of me getting a sample proportion at random that includes a confidence interval that doesn't contain P. That is huge. If that made no sense, I hope that you will rewind the last 3 to 4 minutes and replay that over and over and over until it makes sense. And I think it will. I know it will. I've taught this long enough uh, to know that. So what does that left endpoint look like? So again, let's go back to the center. What does this left endpoint look like? It just looks like uh, the negative z alpha over 2 times sigma, but its location is that, because that's that distance from P to here. But I need it from P hat, right? So it's just P hat minus Z alpha, Z alpha over 2 times sigma. What does this right end look like? Well, again, that distance is the same as that distance, but it's centered here, so it starts from P hat plus Z alpha over 2 times sigma. All right, leading us to something very, very, very important, the confidence interval formula. The confidence interval formula is P hat. Again, P hat is the point estimate. So we have our P hat plus or minus the margin of error. The P hat plus or minus our margin of error is always equal to Z alpha over 2 times sigma. And in this case, sigma is P hat times 1 minus P hat over N. Now, notice something. Up to now, I've always told you that that was P times 1 minus P over N. But P is unknown, so I can't use it. So I have to use P hat to estimate that. So in our problem, P hat, if you take 222 over 492, you get this value. Our Z critical for the 95% confidence interval is 1.96. We found that earlier. And then if you put this in your calculator, which is the standard error, is 0.022434. Again, this part right here is the standard error. So each of these components is what? This is our P hat, our point estimate. This is our Z critical for the 95% confidence interval, and this is the margin of error. If I multiply this times this, that is M, which is the margin of error. So I've done the calculations because I have the plus and the minus. I have to do two operations. I have to do this minus the margin of error, and I have to do the point estimate plus the margin of error. So I get two answers. And this answer is the confidence interval. That is the values that I get right here and I get right there in the distribution of sample proportions. So our 95% confidence interval that can be used to estimate P, I can present it as a percentage. I can present it as a proportion, or I may be asked to present it as a sample estimate, point estimate, plus or minus the margin of error. So from this, the point estimate is P hat, which is 0.451. And the margin of error is 0.0440. And again, the margin of error is found by what? The Z alpha over 2 times sigma. All right. As you might expect, there's a much easier way to do all this stuff on StatCrunch. Go to Stat, come to Proportion Stats, and we want one sample. Now, if I had a data set that included these 200 and, well, what was it, 492 subjects, and I had it listed as like yes and no, has a fear of flying, doesn't have a fear of flying, then I would have the data, and I could just go to one sample with data. But I don't have the data. I have a summary given to me. So let's do summary. So the number of successes are the people who reported a fear of flying. The number of observations are the total number of people that we sampled. I am working with a confidence interval now, and I went to 0.95. For reasons I won't go into, we use what's called the standard WALD. You can show your critical value if that kind of stuff interests you. And the confidence interval plot, I don't really remember what that looks like, but I don't remember it to be that interesting. But let's just click it to see. It's not going to mess with any of the stuff, important stuff that we need. So when I go compute, let's see what we got. Moving from left to right, we have a P, which means we're estimating P. Our count is 222 over 492. Again, this is the point estimate. The sample proportion is 222 divided by 492, the point estimate. The standard error, 0.022. Remember that earlier. That's this part. The critical Z, 1.96. Right there. You can see that the left limit of our interval is 0.407. And you can see that the right, well, it calls it the upper limit, is 0.495. So you have to work a little bit to get this, but that should evolve very easily from there. Now, if we come back over, the 95% confidence interval plot really isn't that exciting. The center just comes down to the what was it? 0.4512. That's our p hat. And then this comes to our lower limit, and this comes to the upper limit. So you can come down and get an indication. I don't think it's that interesting, but you may. I don't know. Now, let's take a look at another example. Let's say we've calculated a 99% confidence interval for an unknown P. So we've done all the work. We've thrown our information in StatCrunch, and we've created this confidence interval. So what we can say, first of all, is we are 99% confident, or there is a 0.99 probability that this interval contains P, which is the population proportion, which is unknown. All right. Now, find P hat. Now, remember, P hat is what? It's the value smack dab in the center, because we add the same number to it and we subtract the same number from it to get these two endpoints. So whatever's smack dab in the center is going to be our P hat. So that's going to be really easy. All we have to do is just take 13.6 plus 38.4, just find the average of the two numbers. So my P hat has to be 0.26 or 26%. And this is all I did. I just added the two numbers, divided by 2, and I got that. Now, the next thing we may want to be able to find is the margin of error. Now, remember, the margin of error is what? It's the distance from the p hat to each of the endpoints. So really, all I need to do is take one of the endpoints, and I'm going to take the largest one, 38.4, subtract the p hat of 26, and my margin of error has to be 12.4. Again, this is all I did. I took the 38.4, which was the right bound of my interval, minus the value in the center, which is 26, and I get 12.4. Another way to find the margin of error, it's the large number minus the small number divided by 2. So I would have 38.4 minus 13.6 divided by 2, and you'll see I get the same thing. All right, gang, that's all I got. We're going to dive into the weeds a little bit more, but there would be nothing at all wrong with rewatching parts of this video multiple times because you really do need to get a pretty firm understanding of the framework behind the whys and why nots of confidence intervals. All right, that's all I got.